Hi, my name is Sue. In this lesson, we'll look at solving systems of linear equations in two variables using the elimination method and the substitution method. We'll also look at solving a system of equations in three variables. Linear equations in two variables represent lines when graphed. We can see by their graphs that there are three possible outcomes when solving a system of linear equations in two variables. So the first outcome is the two graphs intersect in a single point. The coordinates of this point give the only solution to the system. In this case, the system is consistent and the equations are independent. This is the most common case. The second case is if the graphs are parallel lines. In this case, the system is inconsistent and the equations are independent. That is, there is no solution common to both equations of the system. And so the solution set is the empty set. The third case is when the graphs are the same line. In this case, the system is consistent and the equations are dependent because any one solution of one equation of the system is also a solution of the other. The solution set is an infinite set of ordered pairs representing the points that lie on the one line. Solve the system by using elimination. The goal of the elimination method is to be able to add the two equations and have one of the variables drop out of the new equation formed. In our example, if we call this equation A and this equation B, if we multiply equation B by -2, then our new equation is -2x plus 8y equals +4. And writing the original equation above it, we have 2x plus 2y equals 6. So we can see now if we add these, then the x's will be eliminated, giving us 10y is equal to 10. So dividing both sides by 10, we get y is 1. Looking back, we see that there's actually two variables to be solved for, so we're not finished when we find the first variable. But since it's the only solution that will actually make both equations true, then it doesn't matter which equation we plug it back into. So I'll choose B since the numbers are smaller. So in equation B, it states that x minus 4 times whatever y is, and in our case y is 1, will give me -2. So simplifying, we get x minus 4 is -2. Adding 4 to both sides gives us x is 2. So if we were to graph these two equations, they would cross at the ordered pair 2, 1. This is our solution to the system of equations, meaning that if I plug 2 and 1 in the first equation, and if I plug 2 and 1 in the second equation, they'll both give me true statements. Example 2. Solve the system by using substitution. The substitution method has a different approach. One of the equations must be solved for one variable, and then that new expression will be substituted into the other equation in place of the variable that the first equation was solved for. The goal is the same as elimination, though, to end up with only one equation that has only one variable so that we can finish solving. So looking at our two equations, it looks like the second equation will be the easiest to solve for x, so that we don't introduce any fractions by needing to divide out a coefficient. So calling this equation A and this equation B, so they're easier to refer back to, I'll take equation B and solve it for x. So if the first step is isolating a negative x, that means I add 4y to both sides. This gives me a positive 4y minus 2. And then multiplying both sides by a negative will give me x equals -4y plus 2. Now to use the substitution method, you have to make sure that you don't substitute the equation back into itself, which is another reason we label our equations. So I will plug equation B into equation A. A states that 3 times x, which is -4y plus 2, plus 2y equals 1. This gives me one equation with one variable. So now I can simplify it to be -12y plus 6 plus 2y equals 1, or negative 10y plus 6 equals 1. So subtracting 6 from both sides gives me negative 10y equals negative 5. So dividing both sides by negative 10 leaves us with y is positive half. Now to find the x value, we actually have three choices. We can plug it back into one of the original two equations, or the new version, which is already solved for x. So I'm going to use that one. X equals negative 4 times what y is. Well, now we know y is a half plus 2. So x is negative 2 plus 2, or x is 0. So these two graphs would cross, and they would cross at the point 0, 1/2. So that is our solution to the system of linear equations. Let's take a look at a linear system of equations that contain fractions. When one or both equations have fraction coefficients, it simplifies solving if we remove the fractions first. So for equation A, the lowest common denominator, or the least common multiple, is 3. So I will multiply both sides of my equation by 3, leaving me with a new equation A that looks like x plus 3y equals 2. Equation B has a lowest common denominator, or least common multiple, of 6. So I'll multiply all three terms, or both sides of my equation, by 6, giving me x plus 3y equals 1. If we multiply equation B by negative 1, then we'll be able to drop out the x values. So it gives us negative x minus 3y equals negative 1. And just rewriting equation A above it, we have x plus 3y equals 2. So by adding these two equations, we'll see that not only the x's drop out, but the y's do as well, leaving us the statement 0 equals 1. This means that the lines must have been parallel, and so there are no solutions in common, because 0 is never equal to 1, and this is a false statement. So they have no ordered pairs in common. So our final solution then would be that there is no solution. If we had ended up with a true statement instead, it would mean that our lines are the same line, and so we would have an infinite number of solutions. Now let's take a look at using the elimination method to solve a system of 3 equations with 3 variables. The first step is to take 2 equations and drop out one of the variables. So I'll call this equation A, this equation B, and this equation C. So if we take and multiply equation A by 2, this will give us 10x minus 4y plus 6z equals negative 18. And if I use equation C with it, I will have 2x plus 4y minus 2z equals 14. Adding these two equations will give me a new equation, which I'll call D. D will be 12x, the y's will drop out, plus 4z equals negative 4. So since I have one equation with the variables x and z, now I need to create a second equation that contains only the variables x and z. And since I have not used equation B yet, I must use equation B. So putting B with A, I can drop out the variable y again by taking twice equation B and 3 times equation A. So let's see what those look like. Twice equation B would be 8x plus 6y plus 10z equals 8. 3 times equation A would give me 15x minus 6y plus 9z equals negative 27. Adding these two equations will give us a new equation. We'll call this equation E. 8x's plus 15x's give me 23x's. My y's drop out, just like in this second equation here. And then 10z's plus 9z's give me 19z's. And then 8 minus 27 gives me negative 19. So now we have two equations, d and e, with the same two variables, x and z. So I'll start a new page and move them over here. Here's d and e. We have our original three equations with three variables because we'll have to come back and use them. So two equations, two unknowns. So looking at d and e, they don't have any factors in common, so we'll have to use a 4 times a 19. So if I take d times 19 and e times negative 4, I'll be able to get rid of z. So d's new equation now looks like 228x plus 76z equals negative 76. And e's new equation, after multiplying through by negative 4, looks like negative 92x minus 76z, so our z's will drop out. But then on the other side, we also happen to have a positive 76. So this leaves us with 136x equals 0. And dividing both sides by 136, we get x is 0. Now I can take and plug x is 0 back into either d or e to get the value of z. So I'll just go ahead and use d. So into d, we'll say that 12 times x, which is 0, plus 4z is equal to negative 4. So this goes away, and I get 4z is negative 4, and finally, z is negative 1. So now we have x and z. I can use any of the original three equations to find what y's value is. So I'll go ahead and just use the first equation. So I'll just use a. And a tells me that 5 times x, which is 0, minus 2 times y, which is what we're looking for, plus 3 times z, and now we've found that z is negative 1, is negative 9. This is just 0, so we get negative 2y minus 3 is negative 9, or negative 2y is negative 6. So finally we have that y is 3. So we have x, y, and z. So our final ordered triplet solution then would be x is 0, y is 3, and z is negative 1. Looking back at the steps to solving a linear system in 3 variables by elimination, we have step 1. Eliminate a variable. Use the elimination method to eliminate any variable using any 2 of the given equations. The result is an equation in 2 variables. Step 2. Eliminate the same variable again. So eliminate the same variable using any other 2 equations. The result is an equation in the same 2 variables as step 1. So step 3 would be eliminate a different variable and solve. So using the elimination method to eliminate a second variable using the 2 equations in 2 variables that result from step 1 and 2, then the result is an equation in 1 variable that gives the value of that variable. Step 4 is find a second value. So substitute the value of the variable found in step 3 into either of the equations in 2 variables to find the value of the second variable. So again, we had 2 equations with 2 unknowns, so we were able to completely solve those 2. Step 5, find a third value. So use the values of the 2 variables from steps 3 and 4 to find the value of the third variable by substituting into any of the 3 original equations. Step 6, find the solution set. Check the solution in all of the original equations, then write the solution set. In this lesson, we looked at solving systems of equations in 2 variables using the elimination method and the substitution method. We also looked at solving a system of linear equations in 3 variables using elimination. Now it's time to go into the homework section and work some problems on your own.